I am doing this video as an overview of some of the important concepts we're going to look at in Chapter 5 with probability. So here are the objectives for this particular section. I looked over some of the key terms and wanted to make a few remarks about those. So we're going to look at what probability is. What is this law of large numbers business? What is an experiment? What is an event? What are the rules of probability? I'm not a big fan of the word rules, but whatever. Probability models, and really related to impossible and certain events, are the rules of probability. Then we're going to look at empirical versus classical probabilities. Oh, too far. All right, so let's go to page 2. So probability. Let's go to the e-text. What is probability? And I think this graph is a good way of thinking about some of the details involved in probability. So what happens if you flip a coin 100 times and you look at the proportion of heads? So now I know what you're thinking. Well, why isn't it a half all the time? And this is because of the difference between experimental and classical probability, which we'll come back to later. But basically, probability, as your text says here, is dealing with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. So that's sort of what probability in a nutshell is about. You don't know exactly what happens in the short term, but in the long term, you can predict with a great deal of accuracy what's going to happen. And notice that as the number of flips increases, the proportion of heads seems to get closer and closer to 1/2, but of course we're not necessarily landing on 1/2 every single trial. And that, ladies and gentlemen, is the law of large numbers. And a lot of what probability does is based on the law of large numbers. So make a note of this. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. And so I know what you're thinking. What are all these words? Well, let's talk about these words. And so probability we've discussed. Let's talk a little bit more about the law of large numbers. Well, I guess we've already discussed that. Let's talk about what an experiment is. So here's the text definition. It's any process with uncertain results that can be repeated. So that's similar to a science experiment, but a little bit different. Anything like tossing a coin, rolling a die, rolling 2 dice, pulling names out of a hat. These are all experiments. You don't know what's going to happen, and you can do the activity multiple times. And so these words are very important. Sample space. This is just a collection of all the possible outcomes, and an event is any collection of outcomes from some probability experiment. So let's think about what could happen here if we roll a die. So you've got outcomes. If you roll 1 die, you could get a 1. You could get a 2, a 3, a 4, a 5, and a 6. That is the sample space. Now, if your experiment is to roll a die once, then any one of these outcomes of that experiment is one of these numbers appearing on the die. As you see in this example, what are the outcomes of the probability experiment? Well, event 1 in your book uses as notation E for event and sub 1 to indicate this is a different event than that event. So if you roll a 1, that's an event. If you roll a 2, that's an event. Any of these are events. And the sample space is the set of all possible outcomes. So I should actually be careful about how I write this. Sample space is the collection of all these critters. That's the sample space. And notice here, how do you define the event E, roll an even number? These are the only possible outcomes from the sample space that are even numbers. So this event is the set containing these possible outcomes. So now you might be wondering, what am I allowed to, what sort of numbers make sense in terms of probability? I didn't mean to go that far. There we go. Well, one rule is that the probability of any event must be greater than or equal to 0 and less than or equal to 1. So let E be any event. So this is fancy notation. P of E, this means the probability of an event must be between 0 and 1 inclusive. If an event is impossible, probability of that event equals 0. If an event is certain, probability of the event equals 1. And the probabilities are allowed to range anywhere between 0 and 1, including 0 and 1. So if we go back to probability of rolling even, that was 3 ways to get an even, 6 outcomes possible, better known as 1/2. So any particular time you roll a die, it's just as likely that you'd get an even number as it is an odd number. So a probability model is given as an example in table 1 here. The possible outcomes of a probability experiment and each outcome's probability. And it's important that it's not a probability model if it doesn't satisfy both rules 1 and 2 of the rules. Oh, I'm sorry, I didn't get to the second rule. The probability of E1 plus probability of, you know what? I'm just going to show you it in the book because it is much prettier than what I can write. So the sum of the probabilities of all outcomes must equal 1. So when you compute the probability of each event from the sample space, you have to get 1. So if we look at this probability model, we don't actually know that it's a probability model until we verify that all of the probabilities add to 1. So let's take a look at that briefly. 0.13 plus 0.14 plus 0.13 plus 0.24 plus 0.2 plus 0.16 is 1, or 100%. So this is, in fact, a probability model. And also note that each probability is greater than or equal to 0, less than or equal to 1. Now, I would suggest if someone walks up to you at the grocery store and says, please verify that this is a probability model, I would suggest you add the probabilities first, because if one of the probabilities is less than 0 or greater than 1, you won't get a sum of 1. And so you can verify that quite quickly. So we talked about impossible and certain events. This isn't in the slides, but it's worth mentioning. There's actually a way to quantify unusual, an event that has a low probability of occurring. And in a lot of statistical contexts, 5% or 0.05 is considered unusual, but that is not some sort of steadfast rule, like the fact that the order of the terms doesn't change the value of the sum when you add. That is a mathematical fact. This is more of a convention. So I wouldn't get too excited about this probability of 0.05 being the cutoff for likely and unlikely. I would state that an event is likely to happen, let's say an event is likely to happen 6% of the time, say, well, that's fairly unlikely, but it depends on the context. I mean, if I'm going to die 6% of the time I go out on my mountain bike, I'm probably going to be pretty scared to go out on my mountain bike, whereas if I'm likely to win the lottery 6% of the time, well, I'm still not very likely to play the lottery because I think that the lottery is something I'll never win. But if that makes sense. All right, what else do we have to talk about here? Go to the next page. Probability model, impossible and certain events. Oh, empirical versus classical probabilities. Let's talk about this. So This is an empirical method of probability. So the probability of an event is the relative frequency, and then this squiggly equals means approximately equal to. So this is the classical probability, which we'll come back to in a moment. But if you determine the relative frequency of an event, so you run an experiment, like let's say you roll a die 10 times, and you want to know how often you get an even, you would roll the die 10 times and record what happens. So let's say you roll a die 10 times, and let's say you get 2, 2, 3, 6, 4, 5, 1, 5, 3, 6. Let's say that that was your sample space. For your, well, let's not call it a sample space. Let's say that those are your results of rolling a die 10 times. So relative frequency of even is 1, 2, 3, 4, 5 even out of 10 outcomes equals 1/2. So for this particular experiment that we repeated 10 times, you got exactly 1/2. Now, if you did this again, and I did not choose these randomly, I just made these up. But if you actually roll a die 10 times and recorded the number of evens, you probably get something close to 1/2, but not exactly. So that's an empirical probability, which may or may not match the classical probability, which is given on the next page of your text. The probability is classically computed as long as you have equally likely outcomes. If an equally likely outcome is one where each and every blessed outcome has the same probability. Stop the video for a moment and see if you can think of an example. Great example is rolling a single die, flipping a fair coin. Each outcome, heads or tails, 1, 2, 3, 4, 5, or 6, are all equally likely. So to use the classical method to compute probability, if you're talking about an experiment with equally likely outcomes, you count the number of ways the event can occur, divide by the number of possible outcomes, which we did earlier with the die. The probability of getting an even in the classical sense is 3 possible ways to get an even when rolling a single die, 6 total possible outcomes. So you divide the number of ways you can get an even, 3, by the total number of things that could happen, 6. And there you go. So I hope this was helpful. Please let me know if something isn't clear and I can be of more assistance, and have a great day.